This is Chapter 8, Section 1, page what? 562. And so the system is, well, once we rewrite it and arrange the x's above each other, negative 3 halves x plus 3y equals negative 15 halves. And then the other equation is 1 half x minus y equals 3 halves. Okay. So if I add the equations here, the x's aren't going to disappear, the y's aren't going to disappear, so I'm kind of out of luck. Right? Does anyone have an idea? Matt? Uh-huh. Awesome. So you did, for example, the bottom equation was y equals 1 half x minus 3 halves, right? And what was the top equation? Okay, so it ends up being y equals 3/10 x minus 5 halves. Okay. By the way, I can tell from the work Matt did, they're not going to be parallel. How could I tell that? Different slopes, right? So that's a good situation. And can I see the graph? Let me take a look. Oh, okay. Well, anyways, if you draw the graph, you'll get the solution. That's the idea. Okay? All right, moving on. That's one way to do it. What else could I do? Barb? Okay. So this is good. We have a graphing approach. Right? And so that's what Matt did. We have the idea that Barb had. Is this the variable you solved for? Okay. You did what's called substitution. And the idea is solve for a variable and then substitute into other equation. And so basically, when I teach substitution, I do this. I write the equations next to each other. Okay? What's that? Got the graph? Cool, I'll take a look in a sec. So I write the equations next to each other. I do a little bit of work, and I get y equals, we said 1 half x minus 3 halves. That's what you got, Barb? And then what you did was you said, well, if I know what y is, I can come over to the first equation and substitute. So my new equation is going to be negative 3 halves x plus 3, and where it used to say y, what can I write? 1 half x minus 3 halves, right? And now, the new equation only has what in it? X's. And so, more work gets done, and eventually you got x equals what? No solution. Really? Number 7 has no solution? Oh, I find that hard to believe. Oh, I see what happens. Because you get negative 3 halves x plus 3 halves x. Oh, wait a minute. So you're saying that the very next line would say negative 9 halves equals negative 15 halves. Oh, no solution. Why did I pick this one then? Let me go back to these lines. Let me check this out again. Oh, if I divide by 3, Isn't it y equals 1/2 x minus 5/2 and y equals 1/2 x minus 3/2? That's my mistake. So the graphing approach, you would get parallel lines. Okay. Well, that's kind of annoying. Well, it is. It is. There's one other way to do this problem. One other way that I want to mention. Because graphing approach is great, substitution is great. We will return to these techniques in section 8.7. When we come back after Thanksgiving, that first day, I'm going to talk about these techniques again, but I'm going to talk about them even with nonlinear systems. Okay? So we may have things that are not lines that we're trying to figure out where they cross. Okay. So the method that I want to focus on the most today is what we call the elimination or addition method. And I demonstrated it earlier when I added two equations and got an answer to that simple problem on the board. So let's see. I can't add the equations now, but what I am allowed to do is this. I can multiply the bottom equation on both sides by something smart. Do you know what I want to multiply by? Why 3? Right. I mean, 2 is good also. People that said 2, I don't fault you. You say, I want to get rid of fractions. I understand that. But look what happens if we multiply the bottom equation by 3. Let's leave the top equation the same. Negative 3/2 x plus 3y is negative 15 halves. And the top equation, or the bottom equation now, changes. What does it become? Well, 3/2 x, because I multiplied by 3, minus 3y is equal to 9/2. Boy, look at that. There's that negative 15 halves and that 9/2 again, kind of showing up. And now, when I add the equations, what do I get on the left-hand side? Notice everything dropped out, right? 0 equals negative 6/2, which is negative 3. 0 equals negative 3. Hey, by the way, if you get something like 0 equals negative 3, is that always true or always false? That's false. And that tells me no solution. Same thing that the other techniques told me. Okay? So, maybe that wasn't the best example to start with. Or maybe it was. Kind of shows you something here. Okay? So, well, I'd like to find another one, I guess. Let me jump to number 4. Number 4, we have 2/3 x minus 1/5 y equals 3. And I have 1/2 x plus 3/4 y equals 1. And I don't like this problem already. Because why? You have all these fractions everywhere. And so I'm going to say, you know what we did last time? We multiplied the top equation by 3. And by the way, there's a way I'm going to denote that. I'm going to say we did negative 3 times row 2, and that became the new row 2. Okay? Where row 1 is the first equation and row 2 is the second equation. So I'm going to suggest that we multiply these equations by good numbers to get rid of all the fractions, and then we'll figure out what to do next. Okay? So what might we want to multiply that first equation by? Go ahead. So let's see, number 5. And this is page 562, section 8.1. So here you have a system of equations. 1/2 x minus 1/3 y equals -1. And then 2y minus 3x equals 6. Hey, which one did you go for when you said you're going to isolate it?
I started with 2y minus 3x.
And you solve for that y?
Yes, I actually solved for x.
Oh, you solve for x, okay. 2y minus 3x equals 6. And you solve for that x. So we got -3x is -2y plus 6. And so x is positive 2/3 y minus 2. So far, so good? And then I'll write the other equation over here, because I always told you guys, write the equations next to each other when you do substitution. And now, where it used to say x, I'll be able to put that 2/3 y minus 2 in there. So I have 1/2. I have 2/3 y minus 2 minus 1/3 y equals -1. So far, so good? So I get 1/3 y minus 1 minus 1/3 y equals -1. Oh, now I see what you're talking about. Because you get 1/3 y minus 1/3 y, that's 0. So you just get -1 equals -1. Right? And now what? Well, this is where you get stuck, okay? Now, one thing that would actually help you on this one is if you graph the problem, okay? So, let's suppose I wanted to graph this. That's why when I looked at that second equation, remember how you said you solve for x, and you're allowed to do that. I probably would have solved for y, and I don't know if anyone else did that. But if you take the bottom equation and you solve for y, let's see what you get. I think you get y equals 3/2 x plus 3. Isn't that what I get? Looks like it, right? Divide everything by 2 after you move the 3x over. Is this okay? Now, what about the top equation? Well, the top equation, let's solve for y also. Because let's imagine we were going to graph it. All right, so I'd have -1/3 y, because I'm going to move the x to the other side, is equal to -1/2 x minus 1. All right? And if I don't like all those negatives, I could just multiply everything by -1. So I'll do that. 1/3 y is 1/2 x plus 1. Yeah, I'm just doing it a step at a time. You're right. You could just divide by -1/3 and you're all set. Now I have to divide by 1/3, right? But I don't really divide by 1/3. What I do instead is I multiply by something. What do I multiply everything by? By 3. So when I do that, let's see what happens. We're going to take the entire equation here, and we'll multiply everything by 3, and let's see what we get. Well, we just get y equals what? 3/2 x, right, plus what? Okay. So you actually have, right, this equation, I get this green. And the second equation, I get the exact same thing. These are two equations of the exact same line. So let's say you're going to graph the solutions, right? Well, normally what happens is you graph the two lines. Here, so here's, let's say, y equals 3/2 x plus 3. Normally you graph the two lines and you try and look where they intersect. But in this problem, where do they intersect? Well, I guess they intersect all along the whole line because it's the exact same line. Does that make sense, Jack? So you really have infinitely many solutions. And I want to show you how the book writes it down. Okay? The book's going to write down that the solution, this is interesting.
Oh, this one's T.
That's right. It says t, comma, 3/2 t plus 3. Basically, notice that 3/2 t plus, you can put any number you want in for t, and you'll get a solution. Like if I put in a 0 for t, then I could get 0, comma 3, and that is a point that's on the graph. That's right there. But in general, whatever you put in, if you put in x for t, the y-coordinate will be 3/2 x plus 3. Does that make sense? It's just a way of representing infinitely many solutions.